In this video, we're going to be going over momentum, worksheet 1, Roman numeral 2, conceptual question here. Let's get into it. Why is it difficult for a firefighter to hold on a hose that ejects large amounts of high-speed water? If you haven't seen something like this or ever heard of a problem like this before, go ahead and YouTube firefighter hose out of control, I think it is. And that's, you got like a 1-minute video of a rookie trying to do exactly this. So pause this, go watch that, and then come back to that. I'll put that in the comments too, or the description, sorry. Okay, so now that you've gone into that, let's go and let's draw out what this might kind of look like. So I'm going to go ahead and draw a firefighter here as best I can. And I'm going to draw him holding on to a big old hose there. And let me kind of, he's going to be like fighting against, oh gosh, how do I draw? His first leg and then second leg. There you go, something like that. He's going to be like fighting against this, as you can imagine if you're holding onto a big old hose here. And we'll make the hose like tan. So like here's the hose. You know, it would be really good if I like actually knew how to draw, and then I could like teach you how to draw as I'm doing this. But you know, maybe you can figure out how to draw just from watching me and not doing that. Okay, so let's put some arms on this person here. Maybe it's a fire woman, a fireman. Ooh, they got the big muscles on there because they're holding on to this big thing. Well, that's not too bad with the... You just need to scribble like that more. Okay, that's not so bad. We got water coming in here through here, so I'm going to like show that the water's going this way. And then the water comes out, so water comes out. The stream's going to bend eventually here. So I'm going to make it straight at the beginning because we're going to be looking at right when it comes out, and then we know that it like bends down after that. So bends down. This is kind of bad. So it bends down, shunk, like that, yunk, something like that. And the water's going that way just for descriptive purposes there. Okay. Oh, we should put like a hat on this firefighter here. So they got like big brimmed hats with like, oh gosh, how does that, it looks something like that. And that looks like a pilgrim hat, doesn't it? Okay. Yeah, it's close enough. I think there's like some sash on there. You can put some sash on there. And we'll have them a big grin on their face because they're fighting fires. Yes, that's so bad. Okay, so we're trying to figure out why is it difficult for them to hold on to the hose. And if you haven't looked at this already, you can go ahead and look at there's a problem that I made with a solution to this that's incorrect. So you should probably like take a pause and go look at the incorrect solution after you've already made your solution and see if you can see if you agree with that incorrect solution, which the answer should be no, but it's you know, it's fairly convincing. I tried to make it fairly convincing. And this is a kind of a hard problem. It's a very hard problem. So we look at this and we go, okay, why is it hard for them to hold on to it? Well, we can assume, if they are firmly holding onto it, that this person here has a velocity of 0. Great. If they're firmly holding onto it, we'll say that this hose here has a velocity of 0. And we're assuming that both of these are going to stay 0, so you might say the acceleration of the person, the acceleration of the hose is going to be 0. We got water that's being like pumped. You know, there's a huge truck here that pumps that water, if you weren't sure where that comes from. Sometimes it's from the water pressure at the fire hydrant itself. And we have water that is moving, right? We have water that has a velocity over here, an exit velocity, and then we have the water that's got some entrance velocity here. Now, let's go ahead and let's think just for a second. If I have water pumping in here and then the water comes out of the hose, describe the velocity before it comes out of the hose, or just before it comes out of the hose, and just after it comes out of the hose. And you'd probably say, hey, well, the velocity of the water here before it comes out of the hose and after it comes out of the hose, isn't that going to be the same? It would be reasonable, right? Unless it was going through, like, as it goes through, like, kinks and such like that, it's going to be a little bit different. But if it's just the straight section, which the nozzle is always like this metal straight section there, then the velocity would be equal to the velocity before and after it comes out of the hose there. So that if that's true, then I know that the momentum beforehand of the water, we're talking about the water in blue here, has got to be equal to the momentum of the water afterwards, meaning that I have a change in momentum of the water to be 0. Great. Wait, hold on a second. this is kind of getting to my solution from before. If the hose here has a velocity of 0, and both 0 before and afterwards, you might say, well, then the hose has a change in momentum of 0. And let me do the person in a different color. Since the hose is in red here, we'll do the person in green. The green, we had a 0 velocity for him, and we said that he's not going to be moving. He's firmly holding on to it, so then his change in velocity is going to be 0. So then, wait, what's going on here? It looks like everything has a change in velocity of 0. What's going on? So why is it hard for him to hold on to it? Well, let's think about this here for a second. If this water comes, let's think about it loosely, at least a little bit. Let's think about the water coming directly out of the hose. Water shoots out of hose. Water is touching hose, right? Water's touching the inside of the hose there. If water comes out this way, then maybe you could loosely say that this hose is pushing the water to the right. And if the hose pushes the water to the right, doesn't that water push the hose to the left there? Okay. Now, we're saying that slightly loosely there, but that's actually pretty true. Okay. So if a hose pushes water to the right, you could think about the entire length of the hose there, you might say that, because it could go through like little loops and such like that. Then hose pushes water to the right, the water's got to push the hose to the left there. And if you've ever operated a hose before, even a garden hose, when you turn that thing on, you'll feel that it has at least a small or minor amount of kickback there, and that is true. Okay, so then if that's true, if I have, let's go ahead and draw these forces going on here that we're describing. If I have a force on the hose here, force on the hose by the water, it's supposed to be a W. Then equally, I'm going to have a force that's on the water by the hose there. On by notation's helpful. And Newton's third law, just like in number 1 here, Roman numeral 1, that those have to be the exact same. A acts on B, B acts on A. Okay, great. So then let's kind of draw the free body diagram for this person here. So here's the person. So, well, we know that he's going to have some force of gravity going down. Great. He's going to have some normal force going upwards there. Great. If he's not accelerating up or down, we know that those forces are going to be balanced. We just said that he's going to have some force on the hose by the water. I agree with that. But he's touching the hose here, so this is the force on the person by the hose, which is ultimately from the water. And then if he's actually staying in place, he's firmly holding on to that, there's got to be something else going on here. Because if I just leave my free body diagram like this, he's clearly going to accelerate to the left there. And if you watch that video, even when he grabbed onto that, he can actually get accelerated backwards there or to the left. So how does he firmly hold on to it? Well, you got to grasp that thing, obviously, and make sure that it doesn't slip out of your hands there. But then there's something else. Because even if it's not slipping out of your hands, might it knock you backwards still? So you might say, well, I got to lean into it. Great. What else are you doing? How are you putting that force going forwards beyond just the leaning into it? Oh, you got legs here. And notice what did you have to do with your legs? You had to brace yourself, you might say. Oh yeah, what are you doing to the ground here? Oh, I got shoes on. Or maybe I don't have shoes on, but you probably do. I got shoes on here, and these shoes are touching the ground there. And if I'm leaning towards it, I got to make sure that I have good contact here. And if I didn't have good contact, what would happen between my shoes and the ground? Oh, they might slip, and I might slide backwards. What if I operated this hose on a frozen pond, right? I could turn that on, and maybe it'd shoot, and it'd actually cause me to slide backwards there. That would be interesting. That means that something's actually pushing me forwards. Because I'm not sliding, we're assuming he's not sliding, he's firmly holding on to it, that he's got this force that's pushing him to the left here, and so then that's going to be pushing his shoes to the left, but the reason why they're not sliding is because we have friction going on there. Oh, what type of friction between his shoes and the ground? Static friction. Yeah, I would agree. If he's not actively sliding, then he's got some static friction, and that's between his shoes and the ground there, and if I do that in purple like I did before, so then he's got some friction that goes forwards. And it's really on both feet there. And we're just going to add those up and put it as one force there. Now, if he is firmly holding on to it and it's not causing him to fall backwards and such, we know that this must be equal with that one there as well, so that he's not actually accelerating. Okay, great. So then why is it difficult for the firefighter to hold the hose that ejects large amounts of high-speed water? Well, yeah, he's got to be like leaning, he's not got to be firmly grasped onto it in the first place, but he's got to be like leaning into it enough so that it doesn't rotate him backwards. Now, that's something that we're not really looking at in this unit here or this course, but we will in AP Physics next year when you take that. And then he's also got to have like enough grip on the ground there, you might say. Maybe he'd position himself so there's like a little curb here or something like that. So now he can put like a normal force and not just rely on friction there as well. Or maybe he's got like cleats on and he's like in the grass there. You know, I don't think normal firefighters do that, but you could imagine like maybe a firefighter fighting like forest fires or something like that, where they are commonly on porous ground or dirt and such like that. I don't know if they actually do that. I would assume probably not, because they're going to walk on like concrete surfaces at some point. But they might have big treads and such on their shoes, which are doing actually a similar thing there. Those little treads or lugs on the bottoms of those shoes there are going to be digging into the ground, doing a similar thing as a short cleat might do as well. Okay. So then, but like, why is it hard for him to hold on to it? And really, let me challenge myself here and go, is this water really pushing on the hose there? Because didn't we say earlier that the pump is pumping this up? Well, I kind of agree with you on that one. I said, I said before we were like taking a little liberty there. Well, let's zoom out of this picture a bunch and let's take it to kind of like an extreme example here. And I'm going to go ahead and I'm going to draw the Earth there. Why would I be drawing the Earth like this so big? And I could I'm going to mount this water cannon or firefighter hose on a stand here. And we're going to like have it like real big here. So here's the hose and here's, oh gosh, that's the nozzle of the hose. And here's the hose coming back there. And what would happen if I took this hose and we made it really, really high powered, and I have water that comes out of this super high powered hose, and we got water that's, feeding up through there. Water that comes out of the super high powered hose, and it comes out like so fast, such a big velocity that it like goes like that. What might happen? Oh, well, let's see where we get this water from. We're going to obviously get it like somewhere that's on the Earth here. So let me draw the hose like coming into here. And, we'd have to have like a huge industrial pump or something like that to pump all the water up there. But ultimately, what's going to happen? Oh, well, yeah, I got all of this velocity that's in this water here, all of this momentum, you might say, that's coming out to the right there. Huh. Now, if that's coming out to the right there and it's going into outer space there, now I have like momentum that's going to the right there, you might say. Well, then what's also going to have to happen? Because this water, before I started pumping, this water was just down here, and the water had a velocity of 0, and therefore a momentum of 0. Now, can I create or destroy motion or momentum? And the answer is no. We've seen that already. No, we can't create nor destroy, cannot create nor destroy momentum. So then before I turn on the pump, we got total momentum of 0 here for the water. After I turn on the pump, I got now momentum that goes to the right here. So then what else must be true? I must have something going to the left here in the opposite direction that water is ejecting out there. So what would go to the left? And we would say, oh, well, everything that like this is attached to. Let me like define this here as like everything else that is loosely, you might say, pushing the water, but it is all, directly / indirectly pushing that water there. Everything else, so the Earth and the hose and the nozzle and the mount that's there, must be going the exact opposite direction here, must get going that way with some equal amount of momentum that goes that way. Now let's think about this and let's compare these momenta here. We just said that these momentum have to be equal to each other. Okay. Well, let's take a little bit of mass of that water there, and then, well, we got to take the mass of the Earth here. Well, it's going to be gigantic, right? Mass of the Earth there. So now let's think about the water. If we had it, leaving Earth, how fast is that water going to be going? We said before, that's got to be huge, a huge speed to actually leave the Earth. That's like a rocket, being able to get out of the atmosphere, you might say. Well, then, so that's going to be a really small mass of some water, and you might say water in 1 second, you might say, because it's continuously coming out there. So it's going to have a huge velocity, but then over here, I got this gigantic, ginormous amount of mass here. And so tell me something about the velocity of the entire Earth. The velocity of the entire Earth is going to be like incredibly small. Okay, so here we're saying that the total change, I should do this in black, we're saying that the total change in momentum of everything, of the entire universe, you might say. Okay, so in that case, I'm just including the Earth and the water there. The total change in momentum is 0, there, aka we're not creating nor destroying momentum. So that means the momentum before things happen, before I turned on that hose, and the momentum afterwards, they got to be equal to each other. And the momentum before I turned on this hose here and pumped that water, the momentum before was clearly 0. So that means that the momentum afterwards must be 0. Well, that's the momentum of I'll just say the Earth plus the momentum of that water there. And I kind of did it at an angle here, so let's go ahead and let's choose a coordinate plane here. I'll go ahead and choose a coordinate plane at that same angle, so that'll make it nice and easy. We'll say that that's the positive and negative direction, and positive and negative direction. And now if I say that this water is going in the positive direction, this momentum of the Earth, that must be going in the negative direction. Yeah, right, because it's got a velocity there, and that velocity is going to be opposite of that of the water. And so it's going to have a negative velocity for the Earth and a positive velocity for the water. Okay, cool. And so then when I go and do that, this is going to be the mass of the Earth times the velocity of that Earth plus the mass of the water. Again, that you could say like per 1 second. And then the velocity of that water. And I recognize that this is going to be some negative quantity from that velocity, and this is going to be some positive quantity from that velocity, and that's going to add up to be exactly 0. All right, now that's a big case. Can we apply that back to the firefighter case here? Yeah, okay, so let's think about that again. The action here is when he turns on this hose and now it ejects, right? That's like the action in this case right here. So before he turns on that hose, I don't have any velocity here for the water. I don't have any velocity here for the water after it comes out of the hose. But then when I go and turn it on, now I have a huge amount of velocity both before and after it comes in and out of the hose there. Doesn't it look like we just created that momentum all of a sudden when I turned on that hose? Well, we know that that water is coming from some body. It's got to come from some reservoir or lake or something like that, and that's generally stationary in some sort of, let's say, lake for Lake Michigan. That the momentum there of that water is, on average, I agree that there's like waves and such, but on average, you take it over time there, it's going to be basically 0. It's just sitting in that lake there. And I go and start pumping that thing, and now I'm going to shoot water to the right-hand side, and so something's got to be going to the left. Well, the person might be going to the left if they weren't holding it strong enough, if they got let go from them. But now, wait, hold on a second. What if they were able to hold it strongly and firmly? Because we know that firefighters can actually do that. Isn't this then violating the law of conservation of momentum? Because I have water that's shooting out to the right, and it looks like I have nothing going to the left. Something must be going to the left. If now the water is moving to the right, something must be going to the left. What's going to the left? And that's where you're saying, oh, wait, hold on a second. It's like this other example. That's why we zoomed out the picture here, yeah? And we said, okay, if the water's going to the right, that must mean that everything else that's hooked up there and is firmly planted against the ground there, like this stand was, must be going to the left. So that means that this guy or person doesn't have to be sliding to the left because he might be firmly attached to the ground. But that means that the entire ground that he's attached to must be going to the left. Okay. So that means that the whole earth that he's attached to is going to the left. Now, why don't you feel that? Well, that's because the mass of that earth is incredibly large, huge. And so then the velocity must be really, really, really small. Now, going one step beyond this course here, I agree that the earth would go to the left, but there's a little bit more to it. You might say, hey, well, you're doing it like off the axis of the earth here. And so what would it actually do? It would actually cause this earth to rotate. Huh. Yeah, so, and in this case, then the earth would actually start to rotate a little bit to the left there, or counterclockwise in our picture here. Now, again, that amount that it's doing is so incredibly small because the mass is so incredibly large of the earth relative to how fast the water's coming out, the mass of that water per second, you might say. Okay, that one's a pretty hard one to see because this guy's attached to the earth, and so the two things that are interacting are actually the water and the firefighter and earth. There's one thing there so that they're firmly attached to one another. Okay, so that is that does not violate the law of conservation of momentum. It works just fine. Beautiful. Have a great day.